Hello everybody, this is Dr. Bricker here with a review for the first test. So the first exam will be Wednesday from 5 to 6:30. So you'll log into Brightspace, you'll see in the calendar, or you can go to, it's called quizzes on Brightspace. You'll see something called Exam 1, so make sure you're there from at 5 o'clock and it's available until 6:30. So you've got an hour and a half to do it starting at 5 o'clock, so don't be late. It is multiple choice, but you'll have to show your work, so you'll go through, the answers will be there just like the practice test, but you'll have to show your work. If you show no work, you get no points. So keep that in mind. If I were to study for it, I would study the practice test, which you are hopefully have been doing, and you're watching this video. Go back over the homeworks, the PowerPoints, and it's over chapters 20 to 22. So if you don't have time to read all the chapters, at least read the summaries of the chapters. Okay, let's take a look at the actual test. Okay, so it's similar in length. I haven't completely finished it yet, so it's somewhere between 12 and 14 questions. Okay, so 3 equal charges are at the corner of a square. Okay, so here's one, here's one, here's one. A fourth charge of plus q equal magnitude to the other ones is at the center. Okay, so we got this one, this one, this one, then there's another one at the center. Which one of the arrows represents the net force acting on the charge at the center? Okay, so there's a force on the center charge because of the other 3 charges. So let me just call like this one over here 1, this one's 2, and this one is 3. We want to know the force on the center charge because of those. Okay, so they're all positive charges, so they're repelling. We're not worried about what 1 is doing to 2 or 1 is doing to 3, etc. We want to know what's happening to the charge in the center. Okay, so because of charge 1 and the center one, the force on the center one would be this way. That's because of charge 1. So what I'm doing is giving you the direction of the forces on the center charge. Okay, now what's the direction of the charge on the center one because of 2? Well, because of 2, it would be this way. So this one is because of 1, this one's because of 2. Now let's look at what's happening to the center charge because of 3. Because of 3, it's this way, right? So 3 is pushing it to the upper left, 1 is pushing it to the lower right. These actually cancel out because they're the same magnitude of charge and the same distance away. So what we're left with is just choice B here because of charge 2. Okay, so that's a Coulomb force law problem. You'll see something similar to this idea. The formula for this, by the way, the force between charges, K Q1 Q2 divided by the distance between those charges squared. Okay, and remember, like charges repel, opposites attract. Okay, going on to the next one, and this one says explain. So if you just circle the answer with no explanation, chances are you'll get 0 points for that. When a current flows through an ionic solution, such as salty water, the moving charge carriers are. So in an ionic solution, the charge carriers can be both positive and negative. So I can choose choice E there. So I would just say in solution, we can have both positive and negative ions. For example, you could even list some examples. You could have like calcium ion, which is usually, I believe it's usually plus, or you could have potassium or sodium or whatever it is. You can have all these different sort of ions. Now in metals, the charge carriers are electrons. Electrons are free to move through metals. But if you have a solution, you could have both positively and negatively charged ions. Okay, and you can get some partial credit. So you got it wrong, but you had an explanation that makes some sense, you can get partial credit. Same thing like on the first one. You can, if you have an argument there, it might be wrong, but you could still get some partial credit. Okay, choice 3. Negatively charged rod is brought close to but does not touch two neutral spheres that are in contact with each other but insulated from the ground. Okay, so let's kind of draw this. Here's one sphere, here's another sphere. They're touching, and you bring a negatively charged rod close by. So negatively charged just means it's got more negative charge than positive charge. So somebody's added some electrons to this rod. Okay, if the spheres are separated, what kind of charge will appear on the spheres? So when you bring the negative rod close by, that drives electrons to this sphere, leaving this one positively charged. Right, these are conductors, they're in contact with each other. If you bring a negatively charged rod close by, electrons that are in the one that's closest to the rod can move over here. They try to get away from this charge. And then when you separated them, so this is like the before picture. Now you separate these things. The one closest to the rod would be positively charged. The one farther away would then be negatively charged. Okay, so let's see what we have here. The sphere near the rod becomes positively charged. The other one becomes negatively charged. Okay, I think it's choice A. Okay, that's the opposite. Both become positive. The spheres do not get any charge. Well, that's not true. Okay, so good. So choice A, and that's the reason why we've induced this to happen. Okay, good. That's also from chapter 20. The lab has a similar idea going on in the first lab. So 2-point charges, one here. Let me just call that one 1 and 2. Okay, so 2-point charges, 2 microcoulombs and 4 microcoulombs are located at the origin, and 0, negative 0.3. Okay, so that's down here. What is the electrical potential due to these charges relative to infinity at this point over here? So we want to know the voltage at that point. Okay, so the voltage because of a point charge, just in general, is K. So the voltage over here at point P would be K, Q1 divided by the distance from Q1 to the point. That's the 0.4 meters here. Plus the contribution from the other one. So K, Q2, like this one, that's what I mean by 1. That's Q1, that's Q2. Q2, and then the distance to that point. So how far is R2? Luckily we have a 3, 4, 5 triangle here. This is 3, this is 4, so that's got to be 5. It's actually 0.3, 0.4, and 0.5 meters. Okay, then you have everything here. K is just a constant. Q1, don't be careful, it's 2 microcoulombs, so 2 times 10 to the minus 6. And then the distance from Q1 to the point you're talking about is 0.4 meters, so make sure you put 0.4 in there. And then the contribution from Q2. K, Q2, this is 4 microcoulombs, so 4 times 10 to the minus 6th, and then divided by the distance between Q2 and the point we're talking about, and that's 0.5 meters. Now if you didn't realize it was a 3, 4, 5, you would do 0.3 squared plus 0.4 squared, take the square root of that, Pythagorean theorem to get R2. Okay, so put the numbers in there, then you have everything. Okay, so you'll see some kind of voltage problem. Okay, let's look at number 5. A 5 microcoulomb plus 5 microcoulomb charge is placed at the 0 centimeter mark on a meter stick, and a minus 4, so opposite sign, microcoulomb charge is placed at the 50 centimeter mark. At what point on a line through the end of the meter stick is the electric field equal to 0? Okay, so let's call this 5 microcoulomb Q1 and then minus 4 Q2. So remember, whenever you have a positive charge, the electric field goes away from a positive charge and towards a negative charge. So Q1 is bigger than Q2. Their electric fields actually go in the opposite direction. Q1's electric field would be away from Q1. the electric field because of Q2 would be towards Q2. Those effects could cancel out. So it would be something like this. Let me draw a better picture. Here's a meter stick. Here's Q1. Q2 is in the middle. So the electric field because of Q1 is away everywhere. We're looking at the electric field somewhere in here. Right? That's what they tell us from the end. So there's a point out here somewhere where the electric field is actually 0. It's because of the electric field because of Q1 is this way, away from Q1. The electric field because of Q2 is this way, towards Q2. So those are actually equal to each other. So they're saying at what point along the line through the end of the meter stick is the electric field 0? And if you look at the answers, it's always measured from the 0 centimeter mark. So the distance to that point from Q1 is R1. Let's just say that this is the point here. That's the point where the electric field could be 0. Okay, so the distance from Q1 to that point is R1. Really, that's what they're asking in the problem. And then this distance is R2, the distance from Q2 to the point. Okay, so the electric field from the positive charge is away, the electric field from the negative charge is towards. How could they add up to 0? Well, Q1 is bigger than Q2, so the electric field depends on the magnitude of the charge, but that point is farther away from Q1 than it is from Q2, so those effects could cancel out. The effect that Q1 is bigger than Q2 is mitigated by the fact that the distance to the point is bigger for R1 is bigger than R2. Okay, so I'm just looking at the magnitude of the electric fields. They are equal to each other. So this would be K Q1 over R1 squared is equal to K Q2 over R2 squared. Okay? So the magnitude of E1 is equal to the magnitude of E2. Now we just have to figure out, we're trying to figure out what R1 is. So the K's actually cancel out. Okay, so it looks tricky because we don't know R1, but that's what we're looking for. But we also don't know R2. But we do know that R2 plus a half a meter is equal to R1. So we'll have to use that fact to solve the problem. Okay? I'm writing kind of big, so let me go to another sheet here so we can get a clear picture of this. Okay, so this is what I had on the previous page, and we also have this bit of information. R1 is equal to 0.5 meters plus R2. And again, we're trying to figure out, how much is R1. Now, we couldn't get it just from using this equation because there's two unknowns. We don't know R1 or R2. So here's another equation with the same unknowns. When you have two equations with the same two unknowns, we could actually solve that. So we've got to eliminate R2. So let me do a little bit of algebra on the first one here. R2 squared is equal to R1 squared Q2 over Q1. And then I've already taken that absolute value. So Q2 and Q1, what I'm writing now, are both positive. I mean, these are both absolute values. I don't want to keep writing the absolute value sign over and over again. So I've already taken the absolute value. Q2 is plus of whatever number it was before. Okay, so I've just done a little bit of algebra. I'm trying to eliminate R2 from this equation. So I'm going to have to solve for R2 in the first one and then plug it into the second one. Okay, I think my algebra looks okay. So then R2 is R1, the square root of Q2 over Q1. And then I could take that and plug it in here. And then I have R1 is 0.5 meters plus R2, but R2 is this thing, R1 square root of Q2 over Q1. And now I've just got one unknown, okay? That's the only thing I don't know is R1, so I could definitely solve that. Okay, so I've got to get all the R1 terms on one side, so I would have R1 minus R1, the square root of Q2 over Q1, that's equal to 0.5 meters. Writing is getting sloppy here. And again, Q2 and Q1, we know those. We just have to figure out what those are. Clean this up. This is from something I did earlier. Okay. And then I could factor out an R1. 1 minus Q2 over Q1, don't forget the radical there, is equal to 0.5 meters. And then divide both sides by the thing in parentheses. So R1 is equal to 0.5 meters divided by this whole thing. 1 minus the square root of Q2 over Q1. So when you put the numbers in, you get 4.74 meters. Okay, to save a little bit of space, I didn't actually put the numbers in here. So 4.74 meters, that is equal to R1. That's the distance from this charge all the way over to this charge. Now this was a tough problem. This would be a hard one to have on a test. So hopefully it's choice C there. Let's just verify that. Number 5, choice C. Okay, this would be a time-consuming one to have on a test. Maybe a little easier one is if you have a charge here and a charge on the other end. Where's the electric field 0? Well, that could happen if you have both positive charges, for example. Anyway, if you could do number 5, you'll have no problem with the electric field one on the actual test. Okay, very good. So let's see, number 6, this is from the current chapter, no pun intended. We've got 5 amps flowing for 10 seconds. How many electrons? Okay, so don't forget what an amp is. It's a coulomb per second. So you've got 5 coulombs every second. Now I've got 10 seconds. That'll tell me how many coulombs I have. And then I know 1.6 to the minus 19th coulombs. That's the magnitude of charge that one electron has. So I can figure out how many electrons I have. So the seconds cancel out, the coulombs cancel out, and I'm just left with electrons. So when I punch this in, I get 50 on the top divided by 1.6 EE minus 19th, 3.125 times 10 to the 20th. Okay, good. So it looks like choice C here for number 6. Let's just verify. Yeah, good. C. Unfortunately, on the actual test, you won't be able to verify your answer, but in this scenario, we can. Okay, good. So charge delta Q over delta T. So don't forget what an amp represents, a coulomb per second. Next one, 1 meter length of wire has a radius of 0.5 millimeters, resistivity of 1 times 10 to the minus 6th. When this wire carries a current of 0.5 amps, what voltage is across its amp? Okay, so this is from the recent chapter. So the voltage is the current times the resistance. They give you the current in this problem. We just need to know the resistance. So the resistance is resistivity, that's rho, the length of the wire divided by the cross-sectional area of the wire. So if this is the wire, this is the length. They actually give you the length, it's 1 meter. They give you the radius, so we could use the radius to get the cross-sectional area. So the cross-sectional area of this wire is pi r squared. Okay, so you'll have to do a little bit of work to get the area. You can do that, but we have everything. Just be careful of the units. They give it to you in millimeters. So the radius is 0.5 millimeters. So 0.5 to the minus 3rd meters. Okay, so you'll have to do a little bit of work then, as I said, to get the area, but you can do that. The length is given in the problem. Actually, it's easy. It's 1. Resistivity is given also, rho. Remember, the resistivity is just based on what it's made out of. Okay, so all these are given. You can get the resistance, and then use the resistance with Ohm's law and the current to get the voltage. Okay, good. How many electrons are necessary to produce 1 coulomb of negative charge? So how many electrons? So you need 1 coulomb. You know, we need 1.6 to the minus 19th coulombs, magnitude-wise. That's a 19 for 1 electron. Okay, so when I punch this in, the coulombs cancel out. 1 divided by 1.6 EE minus 19th, 6.25 times 10 to the 18th. Okay, so the closest one here looks like this one, 6.3. Okay, good. That was the first chapter. So if it's in this case we have excess electrons. Somebody must have added that many electrons. Okay, let's see what we have here. The force of attraction that a 40 microcoulomb charge exerts on a 108 microcoulomb charge has a magnitude of 4 newtons. How far apart are these charges? So Coulomb force law. K, Q1, Q2 divided by the distance between them squared. So let me call this one Q1. Whoops. This one Q1. This one could be Q2. So Q1 is here. Q2 is over here. And we want to know how far apart they are. So in the formula, the R stands for how far apart are they. We know the force. The force is 4 newtons. There's Q1 and Q2. Let me just write 4 newtons. Okay. I guess I've been writing the variables above the numbers. Like Q1, I've just been writing it above here. I don't know, you don't have to write it above it. You could put it off to the side, like Q1, equal to minus 40 to the minus 6th. Same thing, you could write Q2 there. I'm running out of room. And then put what you need, what you're trying to figure out. Sometimes that's a good way to organize your thoughts. And then we can solve for R. So I'm going to use this formula to solve for the distance between it. So if you have a problem, force, charges, distance between them, you know to use Coulomb's force law. And we're trying to figure out the distance between them here. So R turns out to be K, Q1, Q2, divided by the distance between them. And I'll have to take the square root of that. Okay. So I've just solved for R in that using some algebra. Okay, so you have everything now. Just be careful, it's microcoulombs, which means times 10 to the minus 6th. All right, very good. An electron is accelerated from rest through a potential difference of 1500 volts. At what speed does it reach? Okay, so this goes back to the second chapter that we did, chapter 21. Okay, so how could you actually get an electron to accelerate? Our old friend, the capacitor. So if you shot an electron in here, or I said starting from rest, if you had an electron here, it would accelerate across. So it's starting from rest. So the initial speed is 0. Be careful, we've got velocity and we've got voltage. So this final velocity is what we're actually wanting to know. So you start from rest there, you accelerate across. There's the charge of an electron, there's the magnitude of it. There's the mass of an electron. What speed does it reach? So we're taking electrical potential energy, right? Because the electron doesn't want to be here. It wants to be on the other side, so it's going to accelerate across. So it has electrical potential energy, and we're turning that into kinetic energy. So delta U is equal to minus the change in kinetic energy. Okay, so if I want to, I can write this as 1/2 mv final squared minus 1/2 mv initial squared. Don't forget about the minus sign. Okay, if you want to do it that way. Okay, so we're going from one side to the next, and they say the potential difference is 1500 volts. So be careful with that. It turns out in this one, if the potential difference was 1500, we're going from a lower potential to a higher potential, right? Because this is the negative side, this is the positive side. So delta V in this problem is actually equal to 1500, not minus 1500. It's because it's where you end up on this side, the positive plate, that potential is greater than where you started, the negative plate. So delta V is 1500. Now if you went from the positive plate to the negative plate, and they set a potential difference of 1500, then it would be technically minus 1500. Now if you don't get the sign correct, you'll see later that you must have had something wrong, because you'll have the negatives, you'll be trying to take the square root of a negative, and that won't work out for you. Okay, so this is really physics 220 right here. The new part is this Q delta V part. So this ends up being minus 1/2 mv final squared, because we're starting from rest. The initial velocity is 0. And then, so what do you use for the charge? It's an electron. So this is minus 1.6 to the minus 19th coulombs. So you have everything here. Q, don't forget it's negative 1.6 to the minus 19th. Delta V, that's given in the problem. Q is negative. There's a negative sign on the right-hand side of the equation, so those actually cancel out. It's an electron. They give you the mass, so you know that. Let me try to write one more line here. So you have minus Q delta V times 2 divided by the mass of an electron. Take the square root of that, and that's the final velocity. So there you see the negative sign, but don't forget Q is negative, so that's how it goes away. Okay, good. So you'll definitely have some kind of charge going through some kind of potential. So don't just memorize this little part here. I mean, you've got to apply it to the actual equation that you're using. So this is getting into really the nitty-gritty here, finding the final velocity. Some of the problems on the homework had you just find the change in kinetic energy, and you can get that from not even having to use that whole part. Just don't forget you've got this part. Okay, very good. Next one, each plate of an air-filled parallel plate capacitor has an area. Okay, the area is given. The separation is 0.05 millimeters. There's the electric field strength. Good. Volts per meter, same thing as a Newton per coulomb. What is the capacitance of this capacitor? Okay. So remember, the capacitance just depends on the separation of the plates and the area of the plates. So the capacitance is epsilon naught. So epsilon naught A over D. Okay, that's one way we can calculate the capacitance. It looks like in this problem that's sort of straightforward. We're given the electric field, but in this problem I don't think we actually need it. So capacitance epsilon naught A. The A is actually given. Sometimes the dimensions of the plates are given. You have to calculate the area, and then the plate separation is given. Okay, so A is given. It's in SI units. Make sure you put 0.05 into SI units as well. Okay, so let's. I mean, the electric field's given. What else could we have done with that? This is how to solve this specific problem. So don't forget also, we have that formula for the electric field. This is epsilon naught Q over A. So that doesn't depend on the plate separation. So in this problem, the electric field was given and the area was given. If you wanted to, you could have figured out the charge. Okay, and the voltage across the capacitor is E times D. Now let's see what else can we do with this. So the charge and the voltage on the capacitor are proportional to each other. And then the last one is, remember the charge on a capacitor is proportional to the voltage. I'm giving you everything I know about a parallel plate capacitor, basically. So in this problem, all we needed was this formula, but maybe they ask you for, well, what's the voltage across the capacitor or something like that. Well, if you knew the electric field, you can calculate the voltage, knowing the plate separation. Or in this problem, you knew the electric field in the area, you could figure out the charge. Or you could actually come to this formula too. We know the capacitance, and you know the voltage, you can figure out the charge. So lots of different ways of looking at it. This is everything that we know about electric fields on capacitors, or not just electric fields, everything we know about capacitors, all these different formulas. Okay, let's see the next one here. An electron is moving in the direction of electric field lines. Okay, good. So let's actually figure out a situation where this could happen. So the electric field lines go from the positive side to the negative side. Let me just change the color so I can really illustrate this. This is the electric field. So we know we're going, well, let's see what it says here. The electron moves in the direction, so the electron's going this way. So what's the electron doing if it's moving this way? Well, somebody must have pushed it that way to begin with, or it wouldn't be moving that way. So maybe it was actually, oops, I want to completely get rid of it. Maybe it was shot in here somehow. So an electron is going this way. There's a little hole here in this plate. It enters here. Now it doesn't want to, if the electron enters here with some kind of speed, it's going to slow down. It doesn't want to go to that side. So it's going from a higher potential to a lower potential. Because this is the positive side, this is the negative side. Electric field lines go from higher to lower. And what's it doing when it does that? Well, it's slowing down, so it's losing kinetic energy. It's gaining electrical potential energy. Okay, so let me recap. It's going from a higher voltage to a lower voltage, and it's gaining electrical potential energy. So I think C is the one that actually matches that. Moving from a higher voltage to a lower voltage. I know that because we're going from we're going along electric field lines, which go from higher to lower. And it's gaining electrical potential energy because it's losing kinetic energy. It's slowing down here. So if it's slowing down, it's got to, what's happening to the kinetic energy, it's turning into electrical potential energy. So as far as explain goes, the picture helps out a lot. And I guess I would add to that, moving along electrical field lines, means higher voltage to lower voltage, higher to lower voltage, and then I would also say it's losing kinetic energy and gaining electrical potential energy. Okay, something like that. So this is for an electron. I mean, an electron is going to be slowing down. Now a proton, same thing. We're going from a higher to a lower potential, but it would be losing electrical potential energy because it's gaining kinetic energy. So the first part here is the same. If it was a proton, it's this part here that would be different because it would be gaining kinetic energy and losing electrical potential energy. That's what makes electricity tougher. It's the fact that there's positive and negative charges, tougher than physics 220 stuff. Okay, good. So the choice was C. Let's just make sure. Excellent. The last two are C as well. What is the magnitude of a vertical electric field that will balance the weight of a plastic sphere? Okay, so we've got a plastic sphere. The weight of it's being balanced. So it's something like this. Mg would be pulling it straight down. We've got this electrical force pushing it up. So this goes back to the first homework assignment, actually. So the weight is mg, the electrical force is Q times E, magnitude of the charge. So those are actually equal to each other. So electrical force equal to the weight, mg. So, you know, that's when we first talked about it. What's the use of electric fields? Well, if you knew the electric field strength, multiply it by the charge and you can get the force. Just like in physics 220, if you knew the gravitational field, newtons per kilogram, multiply it by the mass and you can get the force. Okay, so in this problem we're trying to figure out how much is the electrical field. So the electric field then would be mg over q. Okay, this is a negative charge, so the electric field technically in this problem is pointing down, and the force on a negative charge then would be up. Okay, so we have everything here. The charge is given, just be careful. It's nanocoulombs, so times 10 to the minus 9. The mass you've got to put into kilograms. Whoops, I have to circle it. Okay, so it's in grams now, it needs to be in kilograms. So 2.1 times 10 to the minus 3rd kilograms, and then G is 9.8. Okay? So here we have in the last one, 100 watt resistance heater. So this is chapter 22. That's the power. So watts are power. And here's the voltage. How much current flows through the heater? Okay, so we know that power is I times V. We could use that for this problem. It's also equal to I squared times R, or V squared divided by R. We don't need the second two parts of it. We could just use this to solve for the current in this problem. So power divided by voltage will give me the current. Everything's in SI units, which is great. 100 watts divided by 110 volts turns out to be about 0.91 amps. 10 parts in 11. Okay, good. The other thing I'll say about watts, don't forget watts are a joule per second. So some problems, and we did them on the homework, there's a certain amount of, there's a heater running for a certain amount of time. How much energy have you used? Something like that. So just keep it in the back of your mind that what watts really represent, a joule per second. Okay, any questions, email me and I'll talk to you soon.